Hello and welcome back to Math Class in Session. More optimization problems. The steps, which we've learned by now. Example, a boat leaves a dock at noon and heads west at a speed of 25 kilometers an hour. Another boat heads north at a speed of 20 kilometers an hour and reaches the same dock 2 hours later at 2 p.m. When were the boats closest together? Solution, draw a detailed diagram, which is half the problem. Okay, there's a dock, and we have a boat, leaves that dock and heads west. There it is heading west along that line, and it's traveling at 25 kilometers an hour. At any time t, if t represents the time since noon, that distance is 25t. Now it takes 2 hours for the other boat to arrive, so we have to back it up by 2 hours. And it's heading straight north, so it's down here somewhere heading north, and it's taking 2 hours to arrive. So we have to figure that distance at noon is 2 hours of travel at 20 kilometers an hour. So at noon, it must be 40 kilometers away. So when we sub 0 into the expression here for t, we need 40 kilometers because that's its position at noon. And that distance is being diminished by 20 kilometers each hour. So it's 40, take away 20t. And of course, the distance between these two boats is d. And what we need is an expression for d. And we're well on our way towards the first step in the steps. Get an expression for the thing you're trying to maximize or minimize. And Pythagoras helps here. D squared equals 25t squared plus 40 minus 20t squared. And away we go. Squaring them out and collecting like terms. Pause the video and do the math yourself, I suggest. Taking square root both sides, differentiating. And I put the root on the bottom because there's a minus or a negative exponent, which puts this on the bottom, and the 1/2 puts it under a root sign. And we have our derivative simplified somewhat. Now, if we're going to set this derivative equal to 0, we just need to set the numerator equal to 0. Solving for t, and so the time would be 0.78 times 60 minutes is 46.8 minutes, and the time that they were closest together was 12:47. Hardest part of the question, drawing the diagram. Another example, a piece of wire 100 centimeters long is to be cut into 2 pieces. One of the 2 pieces is to be formed into a square and the other is to be formed into a circle. At what point should the wire be cut in order to achieve the maximum and the minimum enclosed area? Area enclosed by a square and a circle. Solution. The 2 pieces of wire will be as shown. This is our 100 centimeter long piece of wire cut here, let's say X centimeters along, and if it's 100 centimeters long, then the remaining part must be the full 100 minus X. If we use a left-hand piece to form the square, it will be a square with side length X over 4. While the circle will have a circumference of 100 minus X. From the formula for the circumference of a circle, which is c equals 2 pi r, we get that 100 minus X equals 2 pi r. So this is the circumference of a circle, and it's equal to 2 pi r. And from this statement follows the fact that 100 minus x over 2 pi must be the radius of the circle we'll get when we form a circle out of this piece. It will have this for a radius. Now we can develop an expression for the area. The area will be the area of a square plus the area of a circle. Now the area of a square will be length times width, and we know that the side length is x over 4, so it's x over 4 times x over 4. Meanwhile, the area of the circle is pi r squared, and we know that r, the radius, is that. And we have our expression for the thing we're trying to maximize or minimize, and we've got it into just one variable, x. Processing it a bit, squaring this fraction, we get x squared over 16, and squaring this one, well, first of all, if we square the bottom, we get 4 pi squared, which reduces with that pi, so we just have 4 pi down here. And then we have to square a binomial, 100 squared, double the product here, so that'll be minus 200x, and then plus x squared. Carrying this forward, differentiating term by term, so it'll be 2x over 16, which is x over 8. The denominator here is a constant, so leave it as a denominator constant. Differentiate the numerator and get 2x minus 200. Set that derivative equal to 0, and I performed the operation of addition of fractions here with a common denominator of 8 pi. So if I multiplied 8 by pi, I have to multiply x by pi. And if I multiply 4 pi by 2, I better multiply each of those by 2. We have a fraction equal to 0, set the numerator equal to 0, and I factored out x out of the first two terms, so that I can now drag this 400 across and then divide by pi plus 4. And we have x. It's 400 over pi plus 4, which on a calculator turns out to be 56. So we have our critical number. Now we have to evaluate the boundaries and the critical points. So we're interested in the a of 0. So plugging in 0 for x and doing the math, we get 10,000 over 4 pi, 795.77. A of the critical number, again plugging in this 56 into the area expression and doing the math, I got 350.06 square centimeters. And finally, the other endpoint, because remember we have to evaluate the boundaries. I said a of 0, that in other words x is 0, and so the cut is right at the very end. And so we're using it all for a circle. And then I made the cut at the critical number 56, and now I'll make the cut at this far end here. So x will be 100. So I'll take a of 100, plug in 100 to the area expression. A of 100 is 625 square centimeters. Looking at the above data, we can find the maximum and minimum. The maximum happens when the cut is made with x being 0. In other words, it's just one big circle. There's no square at all. And the minimum area happens when we use 56 centimeters for the square. A third example, an electric company is located on the opposite side of a 200-meter wide river and downstream from a community of housing that it has contracted to service. It costs the company $40 a meter to lay cable underground and $80 a meter to lay it underwater. It's more difficult. Find the point on the shore it should cross the river to in order to minimize the total cost. Solution, draw a diagram. So let's look at what's going on here. Here's the river, water. It's 200 meters wide. Here's the community, 1,200 meters downshore, or downstream along the opposite shore from the electric company, which is over here. 1,200 meters, that's more than a kilometer. So some wire has to be laid from this electric company to this community across this river. We could go straight across and then all the way along, or we could go straight under the water, straight over to the community, but we want the cheapest one. So at some point here, we'll aim for a spot on that opposite bank, say there. X meters along the other opposite bank. X meters. Now the X could be 0, or X could be 1200, or something in between. And we could label the rest of it the underground part. This will be the underwater part. The underground part, we could label that B, and that will have to be 1200 take away X. And you can check the work by saying, well, if I added these two up, would I get 1200? And of course, yes, you would. Now, a simple expression for the cost will be 80 times A plus 40 times B, because B is underground and A is underwater. Developing this simple expression, we have A is the square root of 200 squared plus x squared by Pythagoras. So A has been replaced by the square root of 200 squared plus x squared. The use of Pythagoras in math class, very popular formula. Meanwhile, B will be very simple. It will be 1200 minus x times 40. And we have an expression for cost in one variable. So we'll have to multiply it out, make it simple. I squared the 200 and multiplied out the 40 over those brackets, expanding and simplifying. Carrying that forward, we now have to do the rest of the steps, which means differentiate 80 times 1/2 of all of this to the minus 1/2 times 2x. That differentiated this term. And then the derivative of 48,000 is 0. That can be ignored. And then minus 40, the derivative of, well, mx. Equaling it to 0 and doing a couple of steps all at once. Well, 80 times 1/2 is 40. This term goes on the bottom under a root sign. I dragged the minus 40 across and joined it with the 0, and 2x remains in the numerator. One might want to pause the video and look and dwell upon this step, and other steps too on these videos. So I equated the derivative to 0 and did some simplifying in one step. Next, take this root, multiply it over here with the 40, and cancel the 40s. Since 40 is a factor of both sides here, they can be canceled, leaving just the root equals 2x. Squaring both sides, collecting like terms, dividing by 3, taking square root both sides, we have a critical number. Now we have to evaluate the cost at the boundaries and the critical numbers. Let's start with an x equals 0. C of 0, plugging it into the cost, we get $64,000. Taking 115.5, the critical number, and subbing it in here for cost. Now I did it on a calculator. It came out to be $61,856. So it's cheaper than going straight across. It's better to go to a point 115.5 meters along the shore. And finally, the cost of going straight over to the company so that the x value is actually 1,200. So C of 1,200 turns out to be a whopping $97,324 to go straight underwater all the way. So we'll take the minimum cost. To minimize the cost, the company must aim for a spot 115.5 meters upstream from their current position, but on the opposite side of the river.